welcome to the current episode of Nested Models. And today we're going to be talking, it's a little bit of a detour. We're going to be talking about generalized estimating equations and covariance models. So to start off, this is what we've talked about at various points. There are three common ways to deal with nested data. Data that has violations of our assumption of independence in the error term that we've been talking about. Fixed effects, we'll be talking about that next week and the week after, and we'll be using fixed effects models quite extensively in the class. Random effects models are the bulk of the class, which will be contrasted with fixed effects models, and at the end, we're going to unify this into a single framework. The sort of the odd duck here is generalized estimating equations, and I would be remiss if I did not describe these in detail. And so that's what we're going to focus on today, and then we're going to also take the opportunity to think a little bit more about covariance matrices, because they're very related to generalized estimating equations. In fact, they're related to random effects models and fixed effects models as well. But we're gonna take a little bit of a deep dive into what they are, so that when we talk about them in random effects models or fixed effects models, you'll have a clear idea of what they are. And they're a tool that we have been implicitly using but not explicitly discussing. So let's talk a little bit about generalized estimating equations. In general, generalized estimating equations belong to a family of models called the general linear model, which is the kind of models that we've always been in, right? So the OLS regression models, where we have some continuous or interval level dependent variable that we're all familiar with, can be more generalized to include a wide variety of models, such as logistic regression or Poisson models or negative binomial models or probit models or log-log models. The list goes on and on. And they're done in this framework that's called the general linear model. And that's why we use things like logits. Logits are linear transformations of nonlinear logistic functions. So if you think about a logistic function, the shape of that S-curve, by taking the log of it, we turn it into a linear function that we can model with simple lines. And that's what we do when we do logistic regression. It's what we do when we do probit regression. It's what we do when we do Poisson or negative binomial regression, is that we convert those with some link function to a linear model. And we'll talk a little bit more about that as we go through this example. But suffice it to say that you have always lived in this general linear model or generalized linear model framework. And the great thing about linear models is that they're additive. So we can easily add variables. They're relatively easy to understand in terms of relationships. We can combine discrete and continuous variables. But the problem that we have with the models that we've learned so far, certainly in previous classes, is that we can't deal with these correlated errors, or the non-independent or clustered or nested or repeated measures or within subjects data. All of these things that we've talked about in this class, these general linear models all have the same problem in dealing with this. We will talk about general linear models in both the fixed effects and the random effects context, but here, generalized estimating equations firmly belong within the generalized linear model family. It extends the general linear model and allows us to analyze correlated data with normal or non-normal dependent variables. So it's just as easy to run logistic regressions here as it is to run continuous or Poisson or a whole host of different kinds of regressions with dependent variables. So generalized linear model or generalized estimating equations are a very functional approach to dealing with correlated data in particular contexts, and we'll talk about that. The DVs are linked to a linear model. So for continuous variables, they are linear models, but for, as we discussed, things like logistic regression or Poisson regression, you have to create a transformation or a link, as it is, to get the nonlinear independent or dependent variables to be linked to the independent variables. And we'll talk about what that means in this context. Suffice it to say, you've already done this, right? So when you run logistic regression, you have a nonlinear dependent variable, right? A non-normal dependent variable that is linked to your independent variables through a link function. You just didn't think about the logistic regression as the logistic regression as using a link function, but here we're going to explicitly discuss that. All right. So let's take a step back. The model we have at the top, where we are predicting some y variable as a function of a mean model, and this is our mean model right here, where we are, and we've talked about this ad nauseum, how we can get the mean of a group as the grand mean with this centered at 0 is this term right here, the intercept, and then we have this term right here, which represents the mean of this group, the difference between the mean, the global mean, the grand mean, whatever this mean is, and whatever this element is. So this is a mean model that we can then calculate any x group here. We then have an error term, right? And what we assume when we make the assumption that our errors are normally distributed, right? So here's normally distributed, independent and not correlated and consistent variance. What we assume is this covariance matrix between each of these observations. So here on the diagonal, we have variances, and we assume that the variance across these guys is all the same. We also assume that these guys, right? So we're talking about the error term here. So we have one variance that we estimate for the error term, right? And that's this guy right here, which there's nothing new about this. This is all the same thing. I'm just showing you in a matrix form. And we assume that these errors, after conditioning on the x, right? So after taking consideration of our x, they're independent. They're not correlated. And this is what these zeros mean, that there's no correlation between them. So the error for variable 1 is uncorrelated with the error for person 1, assuming that these i's are persons, right? The error for person 1 is uncorrelated with the error for person 2, is uncorrelated with the error for person 3. The error for person 2 is uncorrelated with the error for person 3 after conditioning on the x's. So that we assume that we've specified our model correctly and that these errors are uncorrelated with each other, and this is the assumption that you've always used with regression. The problem is, and as we've discussed in this class, is often with nested data, whether it's persons, so it's the J here can be persons and the I would be observations, individual time observations. J could be states and I could be persons. You know, whatever the nesting function is, the nesting structure here is, we know that there is a correlation, and we've called that correlation psi. And so if you think about the models that we've estimated so far, we've estimated a variance, but we've also estimated a correlation between or within subject or within cluster correlation, and that we've called psi here. And so this is what we talked a little bit about last week in terms of the interclass correlation, right? So this is the intra-class correlation, the correlation between or within, the correlation within clusters, right? So this is, if this is a person at time 1 and this is a person at time 2, there's a correlation between them, right? So if we have 3 observations for a person, time 1, time 2, time 3, those observations have a correlation. And we're assuming that we've modeled that correlation using our, in the last week we used variance components models. We'll use a variety of different kinds of models, and today we're going to use generalized estimating equations to do that. But this is all what we've covered before. There's nothing new about this. I'm just showing you in a different way. So there's always been this covariance matrix. So these, I will note, are over persons. There's just i's here. Because we have ij's here, now this assumes within persons. So this, for example, if we have a longitudinal data set where we are measuring persons over time, this is all person 1, and this is time 1, time 2, time 3. And this is the correlation between time 2 and time 3. This is the correlation between time 1 and time 2. This is the correlation between time 1 and time 3. all for person one. So we've switched what the units are. Here we only have one unit, and this is the correlation of the errors over persons or over units of observation. Here it's within the cluster. And so we've switched a little bit. You could extend this out, obviously, and make a more, so each person would have their own complex, it would be a more complex thing to look at because it's a matrix nested in a matrix. But I just want to be clear that we've switched the units here to across all observations to within clusters. And this is the problem that we have. This matrices down here is the problem that the whole class is designed to deal with. How do we deal with these correlations? And today what we're going to do is we're going to treat them as garbage. We're throwing them away. And that's what generalized estimating equations functionally does. With fixed effects models, we explicitly model them. We get a mean for each person with our fixed effects. With random effects, we make an assumption about it and that it's distributed and that we have properly modeled this covariance structure using some function. And we'll have similar functions that we can use that we use for generalized estimating equations. So the covariance structures will move into these other kinds of models. But with generalized estimating equations, what we assume is that this is a nuisance that we don't really care about. And we just want to get rid of it so that we can estimate this mean model better. We just want to get good estimates of our mean model. So if you are just interested in running a usual regression and that this error term here, that it's nested in this J term, whether it's persons or states or whatever, is a problem and just a nuisance for you, generalized estimating equations are a great way to deal with it because they're really simple models to estimate. They're robust to misspecification of this covariance structure, and they include robust standard errors sort of naturally. It's just a really good way of dealing with a lot of the kinds of problems that we have. But suffice it to say, if you're interested in the covariance structure, if you're interested in the effect of the nesting, if you're interested in what's going on here, or you're interested in the units themselves, then we got to think about fixed effects or random effects models. And then there's a few other limitations of generalized estimating equations, but we'll get to that. All right. So generalized estimating equations are great for particular forms of nested data. Didactic relationships, families, schools, and organizational studies are all possible, although I would say that generally those are not the ideal situation. The ideal situation for generalized estimating equations are repeated measures, longitudinal data analysis. And for a lot of you that have longitudinal data and you want to measure it over time, generalized estimating equations are probably the models that you want to run. There's some within subject designs, pre-post designs, and things like that that generalized estimating equations are also good for. So these are very similar. You know, this is the kinds of stuff that we're talking about in our class. Generalized estimating equations treat all of this nesting, whether it's families or schools or persons within time, as a nuisance, and we're just going to model it, get it out of the way, and throw it away. And that's the basic structure of a generalized estimating equation. So how do these things work? First, it's native linear regression analysis, and it's carried out by assuming the observations are within subjects are independent. So the first thing we do is we just run our old, let's assume that we're running a normal regression. And by normal, I mean normally distributed dependent variable. So it's just a regular regression. The first thing we do is we just run that regression. And then we calculate residuals from that model, right? We call it the naive model, and we just take the observed minus predicted, right? And we get a working correlation matrix. So we get that correlation matrix, that within cluster correlation matrix, and we just estimate it from the actual residuals. So it's an empirical based system. We calculate a model that we know is wrong. That's the first model. We then figure out how it's wrong by calculating the covariance structure or a correlation matrix. Correlation and covariance matrices are the same thing. They're just transformed. The covariance is in the natural units. Correlations are in units that are bounded between -1 and 1, as you're well aware. So we then estimate a working correlation matrix from the observed data that we know is wrong. And then we refit the regression, correcting for that correlation. And then we just keep going back and forth until we have worked out all of that correlation and we've gotten rid of it from the model. In this context, within subject correlation structure, right, the correlation within persons, within classes, within states, whatever, is treated as a nuisance, essentially as a covariate, and we just model it out, and it's gone. We don't look at it generally. Well, ironically, we'll look at it today, but in general, what we're going to do is we're just going to get rid of it, and that leaves the basic mean model that we've always used. And so we treat the regression coefficients just like we always treated regression coefficients. We interpret them the exact same way we've interpreted them the entire time. There's a few little nuances about the estimation. So it's not exactly a likelihood equation. It's a penalized likelihood equation here. But so some things like the likelihood ratio test that we talked about last week, you can't do here. But basically everything else is exactly the same. And all of the software that we are using in this class, whether it's Stata, and we'll go through the Stata commands, or R, the command is called GEE, the package is called GEE. In SAS, it's GenMod or Glimix. Both of them will fit generalized estimating equations models. And they're really straightforward. And there's reasons why you should love generalized estimating equations for correlated data. So compared to linear mixed models or random effects models, we don't assume that the dependent variable is normal or that it's linearly linked to the predictors. You can model DVs that are binomial, multinomial, Poisson, negative binomial, and more and more and more and more. There's a ton of different things, proportions and all sorts of stuff you can do in generalized estimating equations. And that's just our generalized linear model, right? So we're just extending the generalized linear model to allow for correlated within unit or within cluster data. So it doesn't require that repeated responses have a multivariate normal distribution, often, which is never going to happen when you, or rarely going to happen when you have binary or count data. So it's just really flexible to whatever dependent variable that you have. It uses all available data as a default rather than complete cases only. So I'm going to talk about FEMBL when we talk about structural equation modeling approaches to all this and the benefit of that with missing data. So it treats all data as available and uses all complete data rather than just all data rather than just using complete data. It makes it easy to report results. You do it just like you would do a regression or a logistic regression or whatever kind of model you run. It's not sensitive to misspecification of the within cluster covariance structure. And we're going to ironically talk about ways that we can differentially model this covariance structure here. But in general, because of the empirical nature of it, because it uses the actual residuals to model the covariance structure, you can impose something on it and get a little bit more precision. But in general, the covariance structure is going to be modeled reasonably well, and it's going to be robust because we're using the actual residuals. We fit a model, we assume that it's going to be wrong because there's within cluster correlation that we know. We're going to look at the within cluster correlation, we're going to model that within cluster correlation, and we're going to model it away. We're going to throw it away at the end, but we're going to be able to get at least an empirical estimate of what that correlation structure is. The generalized estimator, generalized estimating equation estimator, try saying that fast, is consistent whether or not the within subject associations have been correctly modeled. And that's that robust thing that I was just talking about. That is, we get good values for our beta, we get the true values for beta, and we get, which is the mean model, right? That's the means that we've been talking about, that we've been trying to get. And we also get good standard errors. The robust standard error piece, but also because we've modeled away the within cluster covariance, we can get rid of the problems that we identified early on, and we're left with a nice mean model. So if you just want to run a regular regression and these within subject correlations are a nuisance rather than a thing that you're interested in, generalized estimating equations are a great solution for you. All right. So generalized estimating equations is for the marginal, not the conditional inferences. And this is an important piece. It's less important when we're thinking about models with continuous dependent variables. These models are functionally the same. But once we move to logistic regression or Poisson regression or any of these others, then there's a difference between the conditional and the marginal model, and we'll talk about this more later. But suffice it to say right now that generalized estimating equations is just estimating the marginal. So I don't want to be too obtuse about this, but what that simply means is that we're not, if we have units, if we have persons clustered if we have persons measured in time, so we have a longitudinal study and we measured people at 4 time points. We are not estimating the effect for each person. We are averaging the effect over all the persons. So again, that's the mean model, right? We're averaging over everybody. We're ignoring the within-person correlation. So the within-person stuff is the conditional model. The between-person stuff is the marginal model. It's generalized estimating equations are the marginal model. The idea here simply is that we're modeling the mean responses, the expected value of y over all the cases, treating the covariance matrix as a nuisance. And so we'll talk more about the difference between marginal and conditional as we move across, as we move through the course. All right. So for something like the logistic regression, and here we're talking about the idea of the link function here. So the expected value of y is the probability that y is equal to 1, right? So that's what we're estimating when we estimate something like a logistic regression. And that has this probability function of mu ij here. By taking the logit of it, we can turn that into a linear function with a mean and a set of covariates, right? And then we can add that. And this is all you do when you do a logistic regression. But what you're doing is you're taking this and you're using the logit as the link function, which enables you to create this linear equation. Otherwise, this probability here is a nonlinear function. That's the S function that you see. It's more like that, right? No, maybe I can draw it, right? That's the benefit of using this kind of thing. So a logistic regression looks like that, right? That's a nonlinear function, right? It's not a line. I mean, it's a curvy line, or not a straight line, right? So what we want to do is turn it into a straight line, and that's what this stuff here does. That's what taking the logit link does, is it turns this curvy line into a straight line, and the straight line can be modeled using our old linear additive model here thing. Otherwise, we have to do a multiplicative model, and we never want to get in multiplicative models. They're confusing. We can model that, and we get our odds ratios. We'll talk about this later. I don't want to spend too much time on it, but let's suffice it to say, this is just our friendly old logistic regression at this point. The key here is that there is some link function, in this case a logit, that we use. So the bottom line is, if the scientific focus is on the regression coefficients, the betas, the mean structure of the model, then using this reasonably approximate covariance structure that we're going to estimate directly from our model is a totally great way of dealing with this problem. We get our betas, we get our robust standard errors that understand this covariance structure, and that allows us to just interpret our model the way we would any old regression, and we'll look at that in a little bit. So the standard errors are where the problem comes with the dependence, and when you have a lack of independence between observations, our standard errors will be too small. And intuitively, this makes perfect sense. If I assume that each observation in my data set is independent, but my data is clustered, so for example, I'm measuring persons over time, well, I am more similar to myself over time, which will make my standard errors smaller, right? The within subject standard error is going to be smaller than the between subject standard errors, because I'm more similar to me at time 1 and time 2 than I am to you at any time point, right? So, but if I assume that we're exchangeable, like what we're really looking at is me to you rather than me to me to me to me to you to you to you to you, then what we'll do is we'll estimate smaller standard errors. Smaller standard errors are going to produce are biased or wrong, right? That's not the true standard error in the population because we've assumed independence and we don't have independence. So we have to account for this within subject variability in order to properly estimate the standard errors. And that's what this says, that we will underestimate the true variance. And so essentially you're cheating, right? Like you're gonna have the standard error if you've got 4 times as much. You essentially have, if you have 4 observations, you have 4 times as much data that's shared within itself than you really think. And so this presents a problem that we have to deal with. So now we're going to talk about different types of covariance or variance covariance matrices. And again, we are talking about the within cluster covariance, the shared covariance that violates our assumption of independence. So maybe we have, in this case, time 1, time 2, time 3 for a single person with the variance. We've assumed that there's no shared variance between this, but we know that if I'm measuring a person at time 1, time 2, and time 3, that there is going to be a shared variance. So this 0 is wrong, but we have assumed the 0 is correct. What generalized estimating equations does in general is using the sort of iterative process that we described before, where we assume naively that there is no covariance. We fit a model, we look for the covariance, we then model the covariance, allowing A, B, and C to have some non-zero value, right? So that represents the correlation between our time observations within person. And in general, we can tell it to estimate a lot of different kinds of correlation structures. And that's what we're going to talk about here, is the different kinds of correlation or covariance structures. And again, I'm using covariance and correlation totally interchangeably. They're just scale differences. We're gonna think about what we want to have here by thinking about what the relationship is within the unit, within the cluster. All right, so there are a whole bunch of correlation structures we can have. I will note that this is the within subject correlations that we're talking about here. And the good thing is generalized estimating equations, unlike the models that we're going to talk about later in the class, is fairly robust to being wrong about the choice of the correlation matrix. Particularly when you have a large sample size and you have balance within subjects. So meaning that everybody in the data set is measured at 4 time points. And if you have 5 or 6 time points, you're gonna do well as well. You don't want too many. You want a lot of subjects and fewer within subject observations in general in generalized estimating equations. But we want a large sample size to accurately estimate that covariance structure. But we have a lot of choices, and we're going to talk through them. So there's independence, there's exchangeable, there's autoregressive, which is a great one if you have people in time. You have independent, and then totally unstructured. And so there's a variety of different ways that we can think about it. I will note that the exchangeable correlation structure is generally what we have when we have random effects models. So that's what our models last week, we were making an assumption of exchangeable correlation structure. And we'll talk about what all these mean. All right. So we're looking for the simplest structure that fits the data well, as we always do. We're always concerned about degrees of freedom or how many parameters we have to estimate. The more parameters you estimate, the more data you need, the more complex the model is, the fewer the parameters you estimate, the better in general, although you need the appropriate number of parameters to model the data. So there's a trade-off between precision and simplicity or sample size. So here's independence, and that's what we've assumed, right? That there's going to be some variance here, but that there's no relationship between the observations. These dots here just get rid of the variance structure so that we don't have to see the variance. So we're just looking at the covariance. We're just looking at these zeros here. And independence assumes that there's no relationship. You'll note that that is what you've always assumed. So this is the covariance structure that you've always assumed for models. Exchangeable is the basic one that we assume with most multi-level models, which is that there is a correlation. A correlation. There's no subscripts here. There's just a correlation that reasonably represents the relationship between all of the variables. So this is also known as compound symmetry, and there's only one degree of freedom here. We're only estimating one parameter, which is the correlation. So that means that each person at each time point, the correlation within each person at each time point is going to be functionally similar, that the relationship within cluster is the same. So there's no change over time, that the relationship between time 1 to time 2 is the same as the relationship between time 1 to time 3, that there's no decay in that relationship, that there's invariance to time. Which is a safe assumption if you're talking about kids in school. There's probably some teacher effect or class effect that is reasonably estimated and works perfectly well across units, that this single parameter estimate is probably a pretty reasonable one. Time is a little bit different, right? So while I am more similar to myself at time 1 to time 2 than I am to you at time 1, right? There is with in-person correlation that matters. You and I might be exchangeable, but I am certainly not exchangeable with myself compared time 1 to time 2. But my time 1 is probably more similar to my time 2 than my time 1 is to my time 3. And so what autoregressive functions allow is this correlation to change over time. I don't know why. Let me give myself a pen here. Is that the relationship of myself at time 1 to time 2 is going to be this rho, but time 1 to time 3 is rho with some decay function, right? And by decay function, I mean just like this relationship is going to be probably stronger than this relationship. It could be reversed, but it's almost always in that direction, right? Like this, my time 1 to time 2 correlation is going to be higher, and then it's going to degrade. And it's going to degrade at some function, and then the same thing is going to happen as I move further apart. So my time 1 to time 4 is going to be lower than my time 1 to time 3, and certainly lower than my time 1 to time 2. So, if you think about most, if you think about ourselves over most reasonable approximations of time, the further you get away, myself last month was more similar to each other than myself when I was 20. When I was 20, there were some differences. Now, there were some similarities. I'm probably more similar to myself at 20 than I am to you. On the other hand, I'm certainly more similar to myself last month than I was to myself at 20. So that is an autoregressive function where there's still a relationship within subject. It's measured by this parameter rho, but we have some decay function that allows the relationship to decrease over time. And then you can specify what that is and where the nature of that decay function is. We can then further specify this by saying that we have one function that happens, one correlation that happens at 1 unit difference. Oh, I'm sorry. So time 1 to time 2, but then a different correlation at time 2 to time 3. And then we might say, okay, by the time you get to time 4, there's independence. So we would specify the dependence, that there's correlation here, a different correlation there, and no correlation there. And that's conveyed by this row with a subscript 1 for one correlation. Here's the one function away, so that's 1 to 3. And that has a different correlation. Then by the time you get to this, that there's no relationship whatsoever, and that is denoted by 0. So this would say that 2 units away have a different correlation from 1 unit away, and that the others are uncorrelated. And you know, you might have situations where that is true. This you'll note is really a function of time. This would not make sense in a classroom setting where student 1 compared to student 2 has one correlation structure, where student and student 2 to student 3 has one correlation structure, but student 1 to student 3 has a different correlation structure. That makes no sense, right? Like, so this is really about variables through time. Another thing that we can do is we can estimate each pairwise correlation separately. And so this might assert that time 1 to time 2 has a correlation, time 1 to time 3 has a correlation, time 1 to time 4 has a correlation, time 2 to time 3 has a correlation, and time 3 to times 4 has a correlation. So you'll notice that here we have 6 different parameters. There's one I missed. What did I miss? So that's 1 to 4, or 2 to 4, that one. So there's 6 different parameters. Here we've estimated 2 parameters. Here we estimate 1 parameter with a decay function, or some function that represents decreasing change over time. Here we have 1 parameter. So we get a lot more precision with the unstructured, but you know, we also have a lot of parameters we have to estimate. So we need a lot of good data in order to estimate this unstructured correlation. In general, we want to have more structure to our correlations because certainly in longitudinal data, you need to think about this a little more. In classrooms, we probably are thinking about exchangeable correlation structures. In states, we're probably thinking about a exchangeable correlation structure. And that's that's the assumption that we make when we do random effects models, is we assume that there's a correlation structure called psi, right, which we've talked about, which was part of our, that's how we get our intra-class correlation. So those are our basic correlation structures. There are many more, and you can look them up. These are the basic ideas. But the idea is that there is a relationship within subject, within persons, within classrooms, within states, etc., that needs to be defined in some ways. The good news is that generalized estimating equations is going to take those pairwise associations and estimate them. Here we would estimate 6 of them, so that's a lot that it has to estimate. And the others it would estimate, in the exchangeable one, it's just estimating 1 correlation. But it's going to do a reasonable job. If the 2 I really like are exchangeable and autoregressive. The 2 I use most often are exchangeable and autoregressive, because they're just generally most applicable. If I have people measured in time, it's pretty reasonable to assume that the relationship between time decays over time. And so it's a pretty simple one, and it doesn't take up a whole lot of parameters. But you want to think about this. And I think that one of the things that we're going to do as we go through the class is we're going to look at this covariance structure, and then there's another one that we're also going to look at. For you SAS people, that's the 2 correlations, the 2 covariance matrices that they talk about. R and G, I believe, is what they call them in SAS. All right. So let's take a look at doing this in Stata. Oh, that's the wrong way. All right, here we go. So let's get some data. We have wage data. So we have persons, subjects, right? We have them measured in various years. We have various things about them, including how much their wage is. And so we're gonna model wage as a function of a couple of things. So here we're gonna model log wages as a function of union membership, whether somebody's married, and the amount of experience. Now, here I have the family. Gaussian is just normal distribution. That's the Gauss distribution, the normal distribution. And the link is itself, identity. If I go to Stata, and I go to statistics, and I go to panel data, and I go to generalized estimating equations, I can see, so this is Gaussian identity. I could do a binomial if I'm doing dichotomous variables. Dichotomous variables. That's a binomial distribution, right? It's a 1, 0. And I can do logit. I can do probit. I can do those would be the two basic ones, logit and probit. If I'm doing a Poisson distribution, I'm almost always doing a log link, negative binomial, a log link, gamma, a log link. Gamma is a good distribution to use. So some of them you use log links. You can use log link for Gaussian, and that's useful for some things. We have our dependent variable in logs here, so that's a little bit different. We have logged the dependent variable as opposed to the expectation of the dependent variable. So a slight difference in interpretation there. But suffice it to say, if I were doing logistic regression, I would be doing logit binomial. That's what you did when you ran your logistic regressions. You were using a binomial family with a logit link. The link is what connects the form of the dependent variable to a linear model, which is why when we run Gaussian, we just have the identity is just itself, right? We're just estimating it to itself because there's no transformation necessary. The Gaussian distribution works as a linear distribution, whereas the binomial needs to be transformed, typically using a logit or a probit link, to a linear distribution. In general, I would not play with these. I would stick with standard ones unless you have some specific reason to do so. And this class is not a class about this. In general, we're going to stick to our standard approaches. So Poisson log, negative binomial log. I would use a log link for a gamma. I might use a log link for Gaussian. That I would do. But for binomial, I would use a logit or a probit link, depending on whether I wanted to do a probit or a logit regression. And there are reasons to do either. All right. So here, because we've logged wage, and if we look at a histogram of wage, we get that's a pretty reasonable normal distribution. There's a little tail over here. But in general, it's a pretty normal distribution. I'm feeling pretty comfortable using just my old Gaussian. I'm making an assumption of an exchangeable correlation matrix. So to go back to our correlations, to our matrices, I'm assuming this one. I'm assuming that the relationship between each person is similar over time. That the wage at time 1 is the same relationship, time 1 to time 2 is the same relationship as time 1 to time 3. That there's a basic relationship that can be defined by a single parameter. That's what I'm assuming here. So we're going to run that. And this is just a normal regression. Now, you will note that if you look, there's a lot of observations within people. This number 13, their wage is going to be more similar than at time 1 in 1980 to 1981 than the relationship of person 13 is to person 17 in 1980, right? Because they're different people. You and I each make different wages. My relationship to my wage last year to this year is probably more similar to me, that within subject correlation is more similar than my relationship to you. We are not, my observations within me are not exchangeable with you. And that's the dependence that we have to model. We've modeled it, we've gotten rid of it, and now we have a set of coefficients that we interpret like we always do. So this is somebody that is not married. This is the log wage. This constant is the log wage of somebody who is not married, because that's 0, not in a union, because that's 0, and has 0 years of experience. It's a log wage. What is the... this is not the right way to do this. This will give us the instead of the mean, the median, because of the transformation out of a log, but whatever, it's close enough, right? So this person is probably making $34,000 a year. So that's the expected value of that. We can see that each, and here's when you have logged your dependent variable, the change in coefficient can be interpreted as a percent change. So union membership gets you a 10% higher wage. Being married gets you a 9% higher wage, and each year gets you a 5% higher wage. And you'll notice that these are just interpreted like regular old regression coefficients. That's it. Done. Now, let's take a look, because Stata gives us the ability to look at the within person correlation, right? So the correlation of time 1 with time 1 is 1, right? That's why there's a diagonal of 1s. What this says is that the correlation that we have estimated for time 1 to time 2 is 0.53. That's a pretty high correlation, so 0.54 essentially. That's a pretty high correlation in time, but we've assumed that that correlation is the same as we move across time. That's probably not true. There's probably some function that changes over time. So here, again, I'm going to do family Gaussian, link identity. That's just a normal old model, normal old regression model. But here I'm going to specify my correlation matrix as autoregressive 1. So that means each unit, each decay counts is going to take 1 unit. So time 1 to time 2 decreases is estimated, and then time 1 to time 3 is going to have a decay. Time 1 to time 4 is going to have 2 units of decay, etc., etc. But I'm estimating a single decay unit. So we can estimate these models here, and we can see that that's pretty good, right? So here we had one parameter to represent the covariance. Here we have a function that decays over time, allowing us to use a small number of parameters, essentially one parameter, right? So the relationship between time 1 to time 2 is the same as the relationship between time 2 and time 3, right? That's this diagonal, right? And then so on and so forth. And so we have an estimate here. The coefficients here are going to stay the same irrespective of the correlation matrix, but the standard errors are going to change a little. So here we have union membership with a standard error of 0.2. Here we have union membership with a standard error of 0.19. So it's a little bit different in terms of that. Experience here is 0.003. Experience here is 0.003. That standard error goes up a little bit. Basically, they're the same. Again, we're pretty robust. Like this is capturing a reasonable degree of the relationship. Here, it's a little more precision. These are going to be better standard errors. This looks like a better model to me. if we want to estimate something, because we have a lot of data, and we have a lot of within-person data, we have 8 observations within person, it's balanced. We could even estimate an unstructured correlational structure. And here's what each of these parameters are estimated themselves. So this is the correlation structure where we have estimated each pairwise relationship gets its own correlation. Wrong way. And here you see, right? So that correlation, that correlation, that correlation, that correlation. This doesn't make a whole lot of sense to me because I suspect that for each averaging over each of the persons, right? So this is not one person, this is over all the people. This is the estimated correlation within person over all the people. That, you know, this difference just probably is a little silly. But there's, you know, and if you can see here why this correlation structure does well, that the one that we just estimated, the exchangeable correlation structure, where we just estimate one parameter, it ends up doing pretty well because, you know, some of these in the lower part are less related to each other. As you know, where you start off is a little less related, but once you get to time 2, you're pretty much in a single place, which is not that different from this. So, you know, looking at all of these correlational structures, I would probably go with this one because it's the simplest, straightforward. And the good news is that our interpretations are totally robust to it. There's very little change in these relationships. Actually, those coefficients do change a little bit, depending on the correlation matrix. There's a little bit of change in that. The standard errors change a little bit. But basically, we're really robust. Like, we're making very similar interpretations. Here, where we're at 0.1, here we're at 0.9. You know, a 9% change versus a 10% change, depending on union membership. So here we have a pretty clear demonstration of the benefits of robust standard errors and generalized estimating equations. These parameters are interpreted just like your standard linear regression models. There's no difference from what you did when you first learned, you know, for the social work students, you know, when you walked into John's class and you started doing regression, the things that you learned about how to interpret these are the same. These coefficients are interpreted exactly the same as you did in that context. A 1 unit change in log wage is associated with a 1 unit change in union membership is associated with a 0.9 change in log wage, which because we logged wage, we can interpret it as a percent change. So moving from non-union to union results in a 9% increase in wage. Being married gets you a 9% increase in wage. Each year of experience is a 5% increase in wage. And so that's exactly how you would have interpreted it in the past. I think these are really useful models. I think that there's a whole bunch of stuff that's left off. When we use generalized estimating equations, there's a few things that are limits to them. Those are just what we did. But there's one additional benefit that I want to mention, which is that generalized estimating equations, like FEML, which we will discuss in a little bit, uses all the pairs. All available pairs are used in the estimation of the model, and in particular the working correlation matrix. So even if you have different sizes of, you know, some people have 3 observations, some people have 4 observations, you're going to get reasonable correlation parameters because it's going to use all available data. Because the long form, you only lose observations that the subject is missing, not all measurements, right? So even if there's one measurement missing, so person 2 has 1, 2, and 4, but are missing 3, you still get all of the pairwise associations. You still use all of the data, and so that's good. So it's a really robust way of handling missing data because you don't do pairwise deletion. So there's a lot of benefits to generalized estimating equations, but there's also limits to generalized estimating equations. It's not a perfect solution to the problem. So it works well when you have lots of subjects or clusters, but few time points or observations. It works less well when you have few subjects or clusters and lots of time points and observations. So if you had a few classes with lots of students, that's not a place to use generalized estimating equations, and that's why you see random effects models so much in research on schools, as opposed to generalized estimating equations. But if you're following persons over time, you have a lot of people, you have few observations, few time points, and so it's a pretty good approach for within time. Now, if you have a bunch of subjects within time, then it gets a little more complicated. Generalized estimating equations requires that there is one within subject correlational structure, and random effects don't require this, and we'll talk more about that and what that means in subsequent classes with random effects. We can estimate separate correlational structures over groups, for example, with random effects, and that's what I've been promising you that we'll do later in the semester when you're not confused enough. And then generalized estimating equations treat the within subject cluster correlation as a nuisance, not something to understand. And often we want to understand what's the effect of, are there different relationships between schools and socioeconomic status? Do different schools differentially affect the relationship between socioeconomic status and reading scores? Remember, we talked about that earlier on. Generalized estimating equations can't do that. Random effects models can. So there's a whole bunch of things that random effects models allow us to do that generalized estimating equations don't. But if you just want to know, did my treatment work? And you want to know over all the people, on average, does treatment A improve outcomes relative to treatment B, then generalized estimating equations are a pretty good method to do that. Now, there are some benefits to random effects models, and we'll talk about what they are in terms of longitudinal data, but a couple of things to get out of today's lecture. One, generalized estimating equations are a good solution when you just care about the mean model and you want to get rid of the covariance structure that violates independence, that it's just a nuisance to you and you just wish it would go away. Well, generalized estimating equations is here to help. They'll just get rid of it. And then you get back to your mean model and you can interpret the coefficients like you have in the past. There's also another point to this lecture, which is that there is a covariance structure behind the data that we're assuming. We've made assumptions of the within subject or within cluster correlation. And that's true of all of the models we're going to run. That's what we're doing in this class. We have taken our error term, as I promised you, and we've understood that there is a relationship within cluster among the errors, and we have to deal with that in some ways. Generalized estimating equations treats it as a nuisance. The fixed effects models it explicitly in a fixed effects parameter, and random effects models is going to treat it as a distribution with a covariance structure that we're going to be able to play with a little bit as we move through the class. But I want you to be aware of that covariance structure. There's another covariance structure we're going to talk about later. That is a little bit of a simpler one, but there's always this within subject correlation structure where we've made that assumption. And so this class is a little bit of an introduction to that in the context of generalized estimating equations. I look forward to talking with you as we move through, and I hope that this provided some helpful instruction on generalized estimating equations.